And now in this lecture we'll answer two questions. The first question, we find out the area of this green triangle, triangle ABC. And in the second question, we find out the length of this line segment AP is equals to x. We have to find out the value of x. So we start with the first question. In the drawing, we have quadrilateral QABCP. We know that AQ equals to AC. We also know that this is angle PQC, that is the right angle. This is angle QPC, that is equals to 60 degrees in size. This is angle ABC, that is also equals to 60 degrees in size. We know that line segment PC equals to 4 units in its length. This is line segment AB, that is equals to 5 units in its length. Again, our task is to find out the area of this green triangle, triangle ABC. So first of all, triangle AQC is an associated triangle because side AQ equals to side AC. QC is the base of this associated triangle, triangle AQC. From the vertex A, we draw perpendicular to the base QC. Again, from the vertex A, we draw perpendicular to the base QC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in the base QC. This point is point M. Triangle AQC is an associated triangle, and we have the rule that says that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So the associated triangle, triangle AQC, the perpendicular AM bisect the base QC. Again, the perpendicular AM bisect the base QC. That is to say, QM equals to MC. It divides the base QC into two equal halves. The first half is QM and the second half is QC. So if we define the first half QM as A, then the second half MC must be also equal to A because they are equal to each other, of course. In the next step, we will extend the perpendicular AM by straight line until it touches side PC. And we will define the touching point of the extended perpendicular AM with side PC. This point is point N. So AM is absolutely, as a perpendicular, it is absolutely a straight line. When you extend a straight line by straight line, the result must be a straight line. When you extend the straight line AM by straight line, the result is AN. So AN must be also a straight line. So if you focus on the right side, of the straight line AM at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AN at point M? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. According to rule 3, of course. In the big triangle PQC, 90 degrees plus 60 degrees is equal to 150 degrees. So 150 degrees plus this missing angle, in total they must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size, because 150 degrees plus 30 is 180 degrees. That is the sum of the angles in any triangle. So this is angle QCP that is equals to 30 degrees in its size. So in the small triangle, small right triangle MNC, this is the small right triangle MNC, 30 degrees plus 90 degrees is 120 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size. According to the sum rule, that says that the sum of the angles in any triangle is equal to 180 degrees. 120 degrees plus 60 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. It's very easy to see that the big right triangle QPC is similar to the small right triangle MNC. Why? Because first of all, this is angle C, that is a common angle that belongs to both triangles. In addition, those two angles are both equal to 60 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and therefore they are equal to each other. So I shall prove that all the three angles of the big right triangle QPC are correspondingly equal to all the three angles of the small right triangle MNC. And therefore those two right triangles similar to each other according to angle similarity rule. So I will write it down. We actually found out that the big right triangle QPC is similar, this is the sign of similar, to the small right triangle MNC, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the right small triangle MNC over side PC of the big right triangle QPC is equal to side MN of the small right triangle MNC. It is actually side MC of the small right triangle MCN over side QC of the big right triangle QCP. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle MNC over side PC of the big right triangle QPC is equal to side this letter is M, so it is side MC. This is side NC over side PC, and it is equal to side MC. This letter is letter M. And it is equal to side MC of the small right triangle MNC over side PC of the big right triangle QPC. NC is the missing side, so we leave it as it is. Over PC. PC equals to 4 units in itself, according to what is given as the question. and it is equals to, it is equals to MC. MC is A according to our definition over QC. QC is A plus A, that is 2A. So in total, we found out that NC over 4 equals to A over 2A. Here we have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the equation, we left only with 1/2. So 1/2 equals to NC over 4. Here we will cross multiply this equation, and we get that 2 times NC equals to 4. Here we divide this equation by 2, and finally we get that the missing side NC is equal to 4 over 2, that is 2. So NC equals to 2 units in its length. NC equals to 2 units in its length. This is the missing side NC that is equals to 2 units in its length. What is the length of the missing side Pn? From the drawing it is very easy to see that Pn equals to PC minus NC. Again, Pn equals to PC minus NC. Pn equals to PC minus NC. So Pn equals to PC, that is 4, minus NC, that is 2. 4 minus 2 is 2. So Pn in total equals to 2 units in its length. Pn equals to 2. In the next step, I'll copy the big triangle ABN. This is the big triangle ABN. In the new page, we realize this big triangle ABN. We know that side AB of triangle ABN is equal to 5 units in its length. This is angle ABC, that is equals to 60 degrees in its size. This is angle ANB, that is also equals to 60 degrees in its size. So actually, this is triangle ANB, that is according to the original drawing. In this triangle ANB, 60 degrees plus 60 degrees is 120 degrees. So 120 degrees plus this missing angle, in total they must be equal to 180 degrees according to the rule that states that the sum of the angles in a triangle is equal to 180 degrees. Therefore, this first missing angle must be equal to 60 degrees in its size. And therefore, triangle A and B is an equilateral triangle. So write it down. Triangle A and B is an equilateral triangle. And we know that all the sides of any equilateral triangle are equal to each other. AB equals to 5, therefore AN must be also equal to 5, and AB must be also equal to 5 units in its length. This is side NB, that equals to 5 units in its length. NB minus NC is CB. Again, CB equals to NB minus NC. So write it down. The missing side BC, that is one side of the green triangle, that its area that we are looking for in this question. CB in total equals to NB minus NC. NB minus NC. So CB in total equals to NB, that is 5, minus NC, that is 2. 5 minus 2 is 3. So in total we actually found out that CB equals to 3 units in its length. This is side CB, that equals to 3 units in its length. In the next step, from point A, we will draw perpendicular on CB. Again, from point A, we will draw perpendicular on the base CB. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CB. This point is point O. We define the length of side AO as H. It is actually the height to the base CB, because it creates 90 degrees with the base CB. So in the next step, I'll copy the right triangle AOB in a new page in order to find out the value of H. That is the height to the base of the green triangle ABC. This is angle ABC that equals to 60 units in its size according to what is given in the question. AB equals to 5 units in its length, also according to what is given in the question. So actually, this is the right triangle AOB that are coming from the original drawing. In this right triangle AOB, sin of 60 degrees equals to AO over AB. So I'll write it down. Sin of 60 degrees equals to AO over AB. AO equals to H over AB. AB equals to 5 units in its length. So in total, we found out that sinus 60 degrees is equal to H over 5. Sinus 60 degrees equals to H over 5. Sinus 60 degrees is square root of 3 over 2. So square root of 3 over 2 equals to H over 5. Here we will multiply this equation by 5 and finally get that H equals to 5 times square root of 3 over 2 units in its length. This is AO that equals to H is equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. So what is the area of the green triangle, triangle ABC? From the drawing it is very easy to see that the area of this triangle, triangle ABC is equals to the base CB times the height of the edge times the height to the base, that is H, over 2. Repeat again, the area of this triangle, triangle ABC, that is the triangle that we are looking for. In this question, the area of the triangle ABC it is equals to the base CB times the height H over 2. CB is 3. We already found out that H equals to 5 times square root of 3 over 2. So it is 5 times square root of 3 over 2 divided by 2. So we have to divide this expression by 2 again. So in total, the area of triangle ABC equals to 5 times 3 is 15. So in total, in the numerator, we have 15 times square root of 3. In the denominator, we have 2 times 2, that is 4. So if you found out that the area of this right triangle, triangle ABC, it is equals to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, it is equals to 6.5 square units in its size. So repeat again, if you found out that the area of this ring triangle, triangle ABC, it is equals to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, the area of this ring triangle, triangle ABC is equals to 6.5 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the length of this line segment AP that is equals to x. We have to find out the value of x. So in the drawing, we have a semicircle. Point O in the center of the semicircle. This is angle PQS, that is a right angle. We know that chord QS is equals to 6 units in its length. Line segment QP is equals to 21 units in its length. This is line segment PO that is equals to 10 units in its length. Again, our task is to find out the length of this line segment AP that is equals to x. We have to find out the value of x. So first of all, we will complete the semicircle to a circle. So completed the semicircle to a circle, and you will extend line segment QP by straight line until it touches the circle. We will define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we will join points S and M together by a straight line. We join points S and M together by a straight line. So by doing all those constructions, we get the peripheral angle SQP. This is peripheral angle SQP. Peripheral angle SQP is equals to 90 degrees in its size, and peripheral angle SQM subtend on chord SM. Again, peripheral angle SQM subtend on chord SM. So here we can implement rule 5. I'll repeat quickly rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. We have in the drawing, this is the circle. This is peripheral angle MAN that is equal to 90 degrees in its size. And therefore peripheral angle MAN subtend on MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. Why? Because in our drawing, this is peripheral angle SQM that is equal to 90 degrees in size, and therefore according to rule 5, it must subtend on the diameter of the circle. Peripheral angle SQM subtend on SM, and therefore according to rule 5, SM must be the diameter of the circle. So I write it down. If we found out that SM is the diameter of this circle, according to what is given in the question, point O is the center of this circle. Therefore, OS is the radius of this circle. We will define the radius of this circle as R. So OS equals to R. Likewise, OM is also the radius of the circle that is equals to R according to our definition. In the next step, we will do another construction, that is to say, from this point O, that is the center of this circle, we will draw perpendicular on QP. Again, from point O, that is the center of this circle, we will draw perpendicular on line segment QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O, and I select QP. This is point N. This is angle M. That is the common angle. It belongs to both triangles. It belongs to the big right triangle SQM, and this angle M also belongs to the small right triangle, NOM. So we define the size of this common angle M as alpha. So we focus on the big right triangle QSM. In the big right triangle QSM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the small right triangle POM, if we focus on the small right triangle NPM, this angle equals to 90 degrees, this angle equals to alpha, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Actually, it is very easy to see that the big right triangle QSM is similar to the small right triangle NON. Okay? So why those two right triangles are similar to each other? First of all, this is angle M, that is the common angle that belongs to both triangles. So we can write down that angle M equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we found that all the figures of the big right triangle QSM are correspondingly equal to all the figures of the small right triangle NOM, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle QSM is similar. This is the side of similar to the small right triangle NOM. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side QS of the big right triangle QSM is equal to side NM of the small is equal to side MO of the small right triangle NOM, side MO of the small right triangle MON over side MS of the big right triangle QSM. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side SQ of the big right triangle QSM is equal to side OM of the small right triangle NOM over side SM of the big right triangle QSM. ON is the missing side, so we leave it as it is, over QS. QS equals to 16 units in its length, according to what is given us the question. And it is equals to MO. MO is the radius of this circle, that is equals to R, over MS. MS is the diameter of this circle, that is equals to 2R. So in total, we found out that ON over 16 equals to R over R. So in this the question, we have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation, we left only with 1/2 equals to ON over 16. So ON over 16 equals to 1/2. Here we will multiply this equation by 16 and finding out that ON, the missing side, ON is equal to 16 over 2 is 8. So ON equals to 8 units in its length. This is the missing side ON. This equals to 8 units in its length. In the next step, I'll copy the small right triangle ONP in a new page, and we will implement the Pythagoras theorem on this small right triangle ONP, on the small right green triangle ONP. So actually, this is the small right triangle ONP that is according to the knowing. This one right triangle ONP, according to the Pythagoras theorem, O and 10 square equals to 8 square plus Pn square. And again, the square of the hypotenuse is 10 square and it is equals to 8 square plus Pn square. 10 square is 100 and it is equals to 8 square, that is 64 plus Pn square. So in total we actually found out that 100 equals to 64 plus Pn square. Here we will subtract 64 from this equation and we get that 100 minus 64 is 36 equals to Pn square. So here we take a root out of this equation and finally get that Pn, the missing sign Pn, is equals to the square root of 36, that is 6. The missing sign Pn is equals to 6 units in its length. This is the missing sign Pn that is equals to 6 units in its length. What is the length of the missing 9797 Qn? From the knowledge it is very easy to see that Qn in total equals to Qp minus Np. Again, Qp minus Np equals to Qn. So I write it down. We actually found out that the missing side Qn is equal to Qp minus Np. So Qn is equal to Qp is 21 minus Np. We just right now found out that Np equals to 6 units in its length. So Qn in total equals to 21 minus 6, that is 15. Qn equals to 15 units in its length. This is the missing side Qn that equals to 15 units in its length. In the next step, we join points Q and O together by a straight line. QO is of course the radius of this circle, which is defined as R. So in the next step, I'll copy the right triangle QOP in a new QON in a new page, and we implement the Pythagoras theorem on this right triangle QON. Actually, QN equals to 15 units in its length, NO equals to 8 units in its length, and only the hypotenuse QO is the missing side. Here by PT is the version for Pythagoras theorem. So actually, this is the right triangle Q and O that they go to the original domain. In this right triangle Q and O, according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse, equals to QN squared plus ON squared. So write it down. QO squared, that is the square of the hypotenuse, is equal to QN squared plus NO squared. QO is the missing side, so we leave it as it is. QO squared equals to QN squared. QN is 15, therefore QN squared is 15 squared, that is 225 plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total, we should find out that QO squared equals to 225 plus 64. 225 plus 64 is 289. So QO squared equals to 289. Here we take a root out of this equation and finally get that QO, the other QO is equals to the square root of 289, that is 17. So if you found out that the radius of this circle QO is equals to 15 units in its length. AO is also the radius of this circle, and AO equals to AP plus PO. AP plus PO. So AO equals to AP, that is equals to X. That is the right segment that we're looking for. Plus PO. PO equals to 10 units in itself, according to what's given us in the question. So in total, we actually found out that AO equals to X plus 10. But AO is the radius of this circle, that is equals to 17. So we substitute AO by 17. And we get that 17 equals to X plus 10. Here we subtract 10 from this equation and finally get that X equals to 17 minus 10, that is 7. 7 units. So we should find out that AP this is 97 AP, this is equals to X, is equal to 7 units in its length. And that is the answer to the second question. So in the next step, I'll some other lecture. I'll start with the first question, of course. Our task in the first question is to find out the area of this green triangle, triangle ABC. So in the drawing, we have polygonal QABCP. We know that AQ equals to AC. This is angle PQC, that is the right angle. We know that this is angle QBC, that is equals to 60 degrees inside. This is angle ABC, that is also equals to 60 degrees inside. Again, we know that we have here also AB equals to 5 units in itself. This is 9 segment PC, that is equal to 4 units in itself. Again, our task is to find out the area of this green triangle, triangle ABC. So first of all, from point A we go perpendicular on QC. Again, from point A we go perpendicular on QC. So actually this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in QC. This point is point M. Triangle AQC is an associated triangle because side AQ equals to side AC. we have the rule that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. We have here, according to the rule that I mentioned, the perpendicular AM to the base QC of the associated triangle AQC bisect the base QC. That is to say, QM equals to MC. So if you define the length of QM as A, then MC must be also equal to A because they are equal to each other. In the next step, we extended the perpendicular AEM by a straight line until it touches the side PC at this point. We define the touching point of the extended perpendicular AEM with side PC. This point is point M. So actually, in the big triangle QPC, 60 degrees plus 90 degrees is 150 degrees. So therefore this third integral must be equal to 30 degrees in size according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise in the small right triangle MNC, 60 degrees plus 30 degrees is 120. Again, 90 degrees plus 30 degrees. First of all, we know that AM is a straight line, and the sum of the angles on this side of the straight line AN at point M must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. 180 degrees. So which angles we have the right side of AN at point M? We have this angle that is the right angle according to our construction. So 90 degrees plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the small right triangle NMC, 90 degrees plus 30 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in its size according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So it is very easy to see that the big right triangle PQC is similar to the small right triangle MNC. Why? Because first of all, this is a common angle that belongs to both triangles, so we can write out that this is the angle C that is equal to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you prove that all the figures of the right big triangle PQC are corresponding equal to all the figures of the small right triangle MNC, and therefore those two right triangles are similar to each other according to angle similarity rule. So if you don't repeat again, actually we found out that the big triangle QPC is similar. This is the sign of similar to the small right triangle MNC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side NC this is side NC of the small right triangle NMC over side PC of the big right triangle PQC is equals to M is equals to MC over QC. Is equals to, actually it is MC over QC. Side MC of the small right triangle MNC over side QC of the big right triangle QPC. But again, we will derive that NC over PC equals to MC over QC. NC is the missing side, so we leave it as it is, over PC. PC equals to 4 units in its length according to what is given us the question, and it is equals to MC. MC is A according to our definition over QC. QC is A plus 8, it is 2A. So in total we should find out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the equation, we have to only with 1/2 equals to NC over 4. Here we multiply this equation by 4 and find out that NC equals to 4 over 2, that is 2. Okay, NC equals to 2 units in its length. This is the missing side NC, that equals to 2 units in its length. What is the length of Pn? Pn equals to PC minus NC. Again, Pn equals to PC minus NC. So Pn equals to PC, that is 4, minus NC, that is 2. So in total Pn equals to 4 minus 2, that is 2. In the next step I copy the big triangle A and B in a new page and analyze this big triangle, triangle A and B. Okay. This is the big triangle A and B that are going from the original drawing. Those two angles are both equal to 60 degrees. So 60 degrees plus 60 degrees is 120 degrees. So 120 degrees plus this missing angle in total must be equal to 180 degrees, and therefore this missing angle must be equal to 60 degrees in its size. So she found out that triangle A and B is an equilateral triangle. So all the angles all the sides of any equilateral triangle are equal to each other. AB equals to 5, therefore AN equals to NB equals to 5. What is the length of the missing side CB? CB equals to NB minus NC. Again, if you found out that CB equals to NB minus NC. So CB equals to NB, that is 5, minus NC, that is 2. So in total, CB equals to 5 minus 2, that is 3. CB equals to 3 units in its length. In the next step, from the vertex A, we do perpendicular on CB. Again, from the vertex A, we do perpendicular on the base CB of triangle ABC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to construction. We define the touching point of the perpendicular from point A and CB. This point is point O. We define the length of AO as H. It is actually the height of the base BC because it gets 90 degrees with the base BC. In the next step, I copy the right triangle AOB in the new page and we analyze this right triangle AOB. I copied it in order to find out the value of H. It is the height of the base of triangle ABC. Okay, this is the right triangle AOB that are going to our original drawing. The opposite AB is 5, AO is H according to our definition. This angle equals to 60 degrees in its size according to what is given as a question. So in this right triangle AOB, according sin of 60 degrees equals to AO over AB. Again, sin of 60 degrees equals to AO over OB. AO is H and AB is 5. So in total, sin of 60 degrees equals to H over 5. Sin of 60 degrees equals to H over 5. Sin of 60 degrees equals to square root of 3 over 2. So square root of 3 over 2 equals to H over 5. Here multiply this equation by 5 and find out that H equals to 5 times square root of 3 over 2 units in its length. Again, if you found out that right edge to the base BC is equals to 5 times square root of 3 over 2 units in its length. Our test is to find out the area of this triangle, triangle ABC. The area of this triangle ABC must be equal to the base BC times the height edge over 2. And again, if you found out that the area of the triangle ABC is equals to the base CB times the height edge over 2. CB is 3. Edge, we only found out that edge equals to 5 times square root of 3 over 2, and we have to divide it by 2 again. So in total, in the numerator we have 3 times 5, that is 15 times square root of 3, over 2 times 2, that is 4. So in total, if we found out that the area of the triangle ABC, it is equals to either 15 times square root of 3 over 4 square units in its size. So in terms of numbers, the area of the great triangle ABC is equals to 6.5 units in its size. 6 points, the area is equals to 6 square units in its size. Here this triangle ABC is equals to 6.5 square units in its size. So I'm finishing the first question. In the next step, I present to do the second question and you solve the second question of this lecture. In the second question, our task is to find out the length of line 70 feet is equal to x. We have to find out the value of x. So in the drawing, we have a semicircle. You know that QP equals to 21 units in its length, QS equals to 16 units in its length. This is side OP that is equals to 10 units in its length. And we also know that angle POQ is equals to 90 degrees in its size. Angle POS, this is angle POS, it is equals to 90 degrees in its size. Again, our task is to find out the length of line 70 feet that is equal to x. So first of all, we completed the semicircle to a circle, and we extended line 70 QP by straight line until it touches the circle at this point. You define the touching point of the extended line 70 QP with this circle. This point is point M. Then join points SM and M together by straight line. So here we created peripheral angle SQM that is equal to 90 degrees in size, and peripheral angle SQM subset of chord SM. So here you can implement Rule 5, repeat quickly Rule 5. According to Rule 5, any peripheral angle that is equal to 90 degrees in size must subset on the diameter of the circle. So in the drawing you have a circle. Inside this circle we have peripheral angle MAN that is equal to 90 degrees in size, and therefore peripheral angle MAN must subset on the diameter of this circle. Here MN is the diameter of this circle. So we can implement Rule 5 in our drawing. Why? Because in our drawing we have this is peripheral angle this is peripheral angle SQM that is equal to 90 degrees in size, and therefore peripheral angle SQM must subset on the diameter of this circle. Peripheral angle SQM subset on SM, and therefore according to Rule 5, SM must be the diameter of this circle. Again, SM is the diameter of this circle. Okay, so the next step so point O is the center of this circle, and therefore OS is the radius R. OM is also the radius of this circle that is equal to R units in its length according to our definition. In the next step we did the construction, that is to say, from point O, that is the center of this circle, we draw perpendicular on QP. Again, from point O, we draw perpendicular on QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O in QP. This point is point N. So here we have we define this angle M as alpha. This is angle M, that is a common angle that belongs to both triangles. It belongs to the big triangle M, the big right triangle MQS. And this is angle M also belongs to the small triangle, small right triangle MNO. So angle M is a common angle that belongs to both triangles. Actually, it is very easy to see that the big right triangle QSM is similar to the small right triangle NPM. So why those two right triangles are similar to each other? First of all, this is angle M, that is a common angle that belongs to both triangles. So I can write down that angle M equals to itself. It's a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you follow now that all the triangles of the big right triangle MSQ are correspondingly equal to the angles of the right small triangle MOP, P, and therefore those two right angles are similar to each other according to angle, similarity rule. Okay, again, if you found out that the big right triangle QSM is similar, this is the sum of similar to the right small triangle NOM according to angle, similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side ON of the small right triangle ONM over side QS of the big right triangle QSM is equal to side MO, side MO of the small right triangle MBO over side MS of the big right triangle QSM. Something again, we derive that ON over QS equals to OM over MS. ON is the missing side, so we leave it as it is, over OS. OS is the over QS. QS equals to 16 units in itself. And it is also equals to MO. MO is the radius of this circle, that is R, over MS. MS is the diameter of this circle, that is equals to 2R. So in total, we should found out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. In this side of the equation, we have to leave 1/2. That is equals to ON over 16. Here we multiply this equation by 16 and find out that the missing side ON equals to 16 over 2, that is 8. This is the missing side ON, that is equals to 8 units in itself. In the next step, we copy the small right triangle ONP in the equation. We implemented on this small right triangle ONP the Pythagoras theorem. This is the small right triangle ONP, this is the copy from the original drawing. This small right triangle, the square of the hypotenuse, that is 10 square, equals to 8 square plus Pn square. 10 square is 100, and it is equal to 8 square, that is 64, plus Pn square. Here we subtract the 64 from the equation and find out that Pn squared, the missing side squared, equals to 100 minus 64 is 36. So the missing side Pn square is 36. The square of the missing side Pn square is 36. Here we do go down the equation and find out that Pn equals to the square root of 36, that is 6. Okay, this is the missing side Pn, that is equals to 6 units in itself. So what is the length of the missing side Qn? Qn equals to P, Qn equals to Qp minus Np. Again, Qn equals to Qp minus Np. So Qn equals to Qp, that is 21, minus Np, that is 6. So in total, Qn equals to 21 minus 6, that is 15. This is the missing side Qn, that is equals to 15. In the next time we join points on Q together by side lines. All Q is of course the radius of the circle, that is equal to R. So copy the right triangle O and Q and O in the new page and represent the Pythagoras theorem on this right triangle Q and O. So here, this is right triangle Q and O, this is a copy from the original drawing. In this right triangle Q and O, QO squared, that is the square of the hypotenuse, equals to QN square plus NO square. QN is the missing side, so we leave it as it is, and it is equals to NO square. NO square. NO is 15, therefore NO square is 15 squared, that is 225, plus NO square. NO is 8, therefore NO square is 8 squared, that is 64. So in total, we should find out that QO square equals to 225 plus 64 is 489. So Qn square equals to 429. Here we took out all of this equation and finally found out that QO equals to the square root of 289, that is 17. So the radius QO of this circle is equals to 17 units in itself. AO is also the radius, that is equals to 17. but AO equals to AP plus PO. And again, AO equals to AP plus PO. So AO equals to AP, that is X, that is the variable that we are looking for in this question. We have to find out the left line segment AP that is equal to X. So AO equals to AP plus PO. AO equals to AP plus PO. AP is X and PO equals to 10. So in total, AO equals to X plus 10. AO is the radius, that is 17. So in total, we found out that 17 equals to X plus 10. Here we subtract 10 from this equation. We found out that X equals to 17 minus 10, that is 7. So if we found out that the length of this 9 segment AP that is equals to X is equal to 7 units. Okay, thank you very much.